Whenever you're trying to figure out where an electron is, there are different stages of where the electron might be. For example, we were talking about in previous lessons, the energy levels of an atom are the rings around the nucleus you can think of. So we got these rings, but within each energy level, there's a sublevel. These are your S, P, D, and F sublevels. But then within each sublevel, you have orbitals. And just as a reminder, S sublevels have 1 orbital, P sublevels have 3, D sublevels have 5, and F sublevels have 7. And then finally, within these orbitals, you can actually finally find the electrons. And just as a reminder, if there are 2 electrons in an orbital, they have to be spinning in opposite directions, which we notate with these half arrows up and down. Usually up is thought about as clockwise and down is counterclockwise. Well, quantum numbers help you specify these electrons' location. So the difference between quantum numbers and electron configuration, which is your 1s2, 2s2, and so on and so forth, electron configuration tells you about all of the electrons, whereas quantum numbers tell you about specific electrons. And now quantum numbers come in sets of 4. So they look like one number followed by another number, followed by another number, followed by another number, usually with commas and parentheses around them. Now, each of these 4 quantum numbers has its own name. The first one is the principal quantum number. It'll always come first. The second is the angular momentum quantum number, and we'll dive into each one of these separately in just a moment. The third is the magnetic quantum number, and the fourth is the spin quantum number. So whenever you're thinking about quantum numbers, these sets of 4 are pinpointing the location of one particular electron. So let's take a look at each of these numbers. Again, that first one is called the principal quantum number, and it is notated N. Well, just like when we were thinking about electrons and rings, N equals the energy level. That is all that the principal quantum number is telling you. So here we have a Bohr model of an atom, and this is, it looks like an atom of carbon. You might be like, yo, Mr. Engel, how are you so smart that you knew that? Well, it has 1, 2, 3, 4, 5, 6 electrons. So that means it must be carbon. Well, if I wanted to know the principal quantum number of one of these blue electrons right here, either one of them, they're both in the first energy level. So the principal quantum number for these blue electrons, N, would just be 1. If I wanted to know the principal quantum number for any of these 4 green ones, their principal quantum number would just be 2. So the second quantum number is the angular momentum quantum number. It's got a very long name, but it's notated by the cursive letter L. And what the angular momentum quantum number is telling you is it's telling you the sublevel. So I've made this lovely little T-chart over here. When L equals, actually let's do that the other way. Let's put sublevel here, and we'll put L over here. So if your electron is located in the S sublevel, we designate that as having an angular momentum quantum number, or an L of 0. If you're in the P sublevel, we give you an angular momentum quantum number of 1. And then this advanced mathematics continues. If you're in the D sublevel, you have an angular momentum quantum number of 2. And if you're in the F sublevel, your L value is 3. So if we wanted to, and here we have an electron configuration, that looks like the electron configuration of fluorine. Again, you might be like, oh my gosh, Mr. Engel, how are you so smart? Well, you have 2 electrons here, 2 electrons here, 5 electrons here. That's a total of 9 electrons, so this must be fluorine. So if we wanted, let's say, to focus on one of these electrons right here, any of those 5, well, our principal quantum number, N, is simply the energy level of that electron, and it's in the second energy level. Our angular momentum quantum number, L, is determined by the sublevel that electron's located in, and this electron's located in a p sublevel, which we said corresponds to a L value of 1. So the angular momentum quantum number is simply telling you the sublevel, and really there's not a good way other than just memorizing this chart. S corresponds to 0, P to 1, D to 2, and F to 3. Now, the third number is the magnetic quantum number, and it's this one that often hangs people up because it's in our applications, it's arbitrary. It oftentimes doesn't matter what our magnetic quantum number is, and I'll explain that. But the magnetic quantum number is notated by M sub L. That's M with that cursive L as a subscript, M sub L. Let me try better L, that's not much better. But why the magnetic quantum number is a little bit confusing is it tells you the specific orbital that an electron is located in. So, for example, if your L value is 1, remember what that means. We'll come back here. Actually, I don't want to start with 1. That's silly. I want to start with 0. We'll come back here, though. If you have an L value of 0, that corresponds to an S sublevel. So if your L value is 0, then you're in an S sublevel. Well, in an S sublevel, there's only one orbital. So there's only one possible M sub L value, and we actually call that value 0. That is the only option. If L is 0, M sub L has to be 0. If your L value is 1, again, we'll come over here. That means you're in a P sublevel. Now, remember, a P sublevel actually contains 3 orbitals, so we have to have 3 possible M sub L values. We designate them as -1, 0, or 1. Now, this pattern continues. If your L value is 2, then you're in the D sublevel, and a D sublevel has 5 orbitals, so our options are -2, -1, 0, 1, or 2. And you might be seeing the pattern. 3 as an L value corresponds to an F sublevel, which has 7 possibilities because it has 7 orbitals of -3, -2, -1, 0, 1, 2, 3. So what you might be seeing here is that M sub L is equal to -L through positive L, including 0. So when L is 3, your possible M sub L values are from -3 to +3, including 0. The fourth quantum number is the spin quantum number. As the name implies, this is notating the direction of the spin of that particular electron. It's notated as M sub S, so M with a subscript of S, and your only options for this number are +1/2 or -1/2. Usually +1/2 indicates clockwise and -1/2 indicates counterclockwise rotation. So here I've got an orbital diagram, or at least part of it. We've got the 1s orbital here, the 2s orbital here, and the 2p orbital here. And this is actually an atom of nitrogen. If I wanted to know the spin quantum number for this electron that I've outlined in green, it doesn't matter what you designate up as. What I mean is it doesn't matter if up is clockwise or up is counterclockwise, though typically we say up is clockwise. We would say that this electron has a spin quantum number of +1/2. Now what's important here is to recognize if you were also asked the spin quantum number of this electron, since these two electrons are spinning the same direction, they have to have the same spin quantum number. So this one would also have to be +1/2. But Mr. Engel, you might say, what if I said that this one is spinning at a -1/2? That'd be fine. But again, since these two have the same spin, you have to notate their spin in the same direction. So we'd also have to say that one's negative 1/2. Where you might run into trouble would be something like if you were asked the spin quantum number of both of these. Then you would have to recognize that since they're occupying the same orbital, Pauli's exclusion principle says that electrons occupying the same orbital have to have opposite spin. So if you designated this up as a plus 1/2, then you would have no choice but to designate this down as a negative 1/2. So let's take a look just at a whole quantum number set and let's see if we can't get some meaning out of it. So here is a set of quantum numbers. Again, this is specifying one specific electron. You have a principal quantum number of 3, so that tells us it's in the third energy level. We see that we have an angular momentum quantum number of 1, so that tells us it's in a p sublevel. We have a magnetic quantum number of 1, and right now it really doesn't serve us much purpose other than to tell us that it's in one of the 3 p orbitals, which if you recall, I'll try to give you 3 dimensions here, 1, 2, and 3. You have 3 different p orbitals. You have one going up and down, one going left and right, and then one coming out of your screen and behind your screen. It doesn't matter which one is designated as 1, -1, or 0, which are our 3 options for p orbitals. That's arbitrary. So for our purposes, we can just say this is 1, meaning this electron was in this orbital. Whereas if we put a 0 here, that would have meant it's in this orbital. Or if this had been a -1, it would have been in this orbital. But the magnetic quantum number is very much arbitrary. And then our last number here tells us our spin. So this 3p electron is spinning clockwise. Okay, so here we have a scenario. 2 electrons in the same atom have have quantum number sets below. Finish the second set. So again, third energy level, p sublevel, a specific orbital of the p sublevel, the same specific orbital of the p sublevel. So you have to recognize here that these 2 electrons are in the same orbital, in which case they have to be spinning in opposite directions. So since the spin of this one is plus 1/2, this one has to have I just wrote a plus 1/2, goodness. This one has to have a negative 1/2 spin. Here we have 10 quantum number sets, and I'm going to be that totally lame person who tells you to pause your video in just a minute and work a problem for me. So I want you to look at these 10, and I want you to pause your video and see how many of them are in the third energy level. You didn't pause your show. I'm still waiting. Excellent. Now that you've paused your show, we're looking for electrons in the third energy level. So all we have to look at is the principal quantum number here. So this one's in the third energy level, this one's in the third energy level, third energy level, third energy level. It looks like we've got 4 of them in that third energy level. So now I want you to tell me how many of them are in S sublevels. So again, pause your video, and I want you to tell me how many are in S sublevels. So S sublevels correspond to an angular momentum quantum number of 0. So we're looking for an L value of 0. So looking down here, looks like this one's got an L value of 0, this one's got an L value of 0, and this one's got an L value of 0. So we've got 3 that are in the S sublevel. And we could do that again this time. Let's just call it the D sublevel. Well, D corresponds to an L value of 2. So looking down our second numbers, our angular momentum quantum number, there's a 2, and that's actually the only one. So there's only 1 electron out of these 10 that's in a D sublevel. And the last one, let's say how many of these are spinning in the clockwise direction. So we'll look for a plus. We got 1, 2, only 2. Looks like the other 8 are spinning counterclockwise. Now, if you're paying close attention, you might have been looking at some of these quantum number sets and thinking that they don't make sense. So one I want to point out to you is this second quantum number set right here. If we think about what all of this means, 1 as a principal quantum number means this electron is in the first energy level. Well, 1 as an angular momentum quantum number, 1 as an L value corresponds to a p subshell. Well, we're in the first energy level. There are no p sublevels in that first energy level. So for that reason, this is an invalid quantum number set. There are no p sublevels in the first energy level. So take a moment again, pause it if you need to, try to find any other sets of these quantum numbers that are invalid. So looking down our list, I see this quantum number set right here. We have a n value of 2, which corresponds to the second energy level, an L value of 2, which corresponds to a D sublevel. Well, there is no D sublevel in the second energy level. So for that reason, this quantum number set is also invalid. Continuing down the list, I notice this quantum number set. We have a principal quantum number of 1. We have an L value of 0, which means it's an S sublevel. But then you have an M sub L value of 1. Well, when you're dealing with the S sublevel, the only possible value for M sub L is 0. So it's impossible to have a 1 orientation of your orbital whenever you're in the S sublevel. So we'll cross that one out. And from a quick glance, it looks like the rest of these might be all right. So moving on to a different idea. Give the electron configuration of titanium. Well, we'll just go through the motions here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So something that you might be asked to do, let's just pick this sublevel right here. So this is the 2p6 sublevel. I want a quantum number set for any of those 6 electrons. So we need to get our quantum number set ready. The principal quantum number tells you the energy level, which is 2. The angular momentum quantum number tells you the sublevel. This isn't a p sublevel, so that gives you an L value of 1. And now you have options here. The p sublevel has 3 orbitals, so you have 3 options for your magnetic quantum number. It can be -1, 0, or 1. It doesn't matter which one you pick in the context of this problem, so I'll just pick -1. That sounds good. And then for the spin quantum number, again, it doesn't matter which way it's spinning. I just want the quantum number set of one of them, so I'll just call it 1/2. Well, I could just as easily then list out all the possibilities here. This could have been 2, 1, -1, -1/2, and these two would be in the same orbital because they have the same M sub L value, but they have opposite spin, so that's good. I could have also done 2, 1, 0, which would just be a different p orbital, plus 1/2. And then I could do that electrons pair, 2, 1, 0, same orbital, but with different spin. I could have done 2, 1, +1, plus 1/2. And then the other electron that would be paired with this one would have a quantum number set of 2, 1, 1, -1/2. Now I want you to notice how many combinations we just had. We had 6 different possibilities down here of quantum number sets. Well, that makes good sense because there are 6 electrons in this sublevel. So there should have been 6 different quantum number sets. And then the last thing would be to look at an orbital diagram, which is our ups and downs in these boxes, just showing the actual spin of these electrons. What if I wanted the quantum number sets of both of these red electrons? Well, just like the previous example, we're dealing with the second energy level, so they would both begin 2. Both red electrons will begin 2. They're in the p sublevel. That corresponds to an L value of 1. Now I have 3 orbitals. It doesn't matter which one is which. A lot of people like to just say -1, 0, 1 just to keep them in order, but it doesn't matter. This third number could just as easily be -1, 0, or 1. Now I do have to call them both the same number though, because they're both within this same orbital. So whatever number I designate here, I have to designate consistently through both of those electrons. And last, that brings us to the spin. Again, it doesn't matter necessarily, but typically up is clockwise, so that would be +1/2, and the other one's spinning the other direction, so it would have to be -1/2. Moving over, though, to these 2 yellow electrons here. If I wanted their quantum number sets, I'll just get my commas ready. They're in the 3rd energy level, so our principal quantum number is 3. They're also in a p sublevel, so the L value is 1. And now again, you have options. You could call this -1, 0, 1, or if you were feeling ambitious, maybe this is 0, this is 1, this is +1, or not +1, that's silly. It'd have to be -1, but it's arbitrary. I'll just stick with what's simple though, and we'll call this -1, 0, and 1. So this first electron is in the -1 orbital, but the second electron is actually in the designated 0 orbital. So we have to show them having different L value, or different M sub L values, because they're in different orbitals. And then the last, this is important not to goof, they are spinning the same direction. So I don't care whether you notate that as +1/2 or -1/2, but you have to notate them the same. And that has been your ever exciting lesson on quantum numbers.